Hello, everyone. Thanks for coming. Today, we're going to have a presentation by Senthil. He's a long-time ARM contributor working for Linaro, and he'll be presenting on TuxMake, which is a tool used for kernel validation.
Thanks, Hector. So let's get onto the talk. So I'm Senthil Kumaran. I work for Linaro Limited for a long time now. So I've been associated with different things. I'm a full committer in Apache Software Foundation. I'm one of it because it's all Git days these days. So today's talk, we'll see about TuxMake with Debian. So the Debian part, I'll come to it later. So it's about TuxMake. TuxMake is a tool which is open source, and we'll see what it is, what it does, and how it's useful for building mainly Linux kernels. So this is the agenda. I'll introduce TuxMake. We'll see the command line. It's basically a command line tool, which we'll see the help and things like that. We'll do a simple build, and I also will show what this build does, the execution details of this, and we'll do cross-compiling Linux kernel with ease using containers, which is the crust of how TuxMake works. And then I'll also show incremental builds, like how it works. And TuxMake is both like command line, and also it provides a library, which is a Python library, which could be used when you're doing different kind of programming inside your Python programs. If you want to use TuxMake, it's also useful. And then we'll, since TuxMake is open source project, we'll see what are the contributing rules and how you can contribute, be part of this tool community. So introduction. TuxMake, as I said, is an open source project with Linaro, which comes with a command line tool and a Python library, which provides portable and repeatable Linux kernel builds. It's specific to Linux kernel builds across variety of architectures, toolchains, kernel configurations, make targets, and stuff like that. TuxMake is part of something called TuxSuite. So I'll come to towards the end of my presentation what TuxSuite is, which is not like so very relevant right now in this conference, but it probably people interested me, like we can take it offline. All these tools we started. So the company which produces this, like Linaro, right? So Linaro is, many of you may already know that. Linaro is one of the major contributors for the ARM ports in Linux kernel. So there are like many kernel engineers who maintain the ARM ports within the Linux kernel tree. And we produce like a lot of tools in order to enable and ease kernel development. And also specifically, Linaro focus on a different side on validation of these kernels for each and every commit which is happening across architectures and things. So TuxMake is based on MIT license. That's why we say it is open source. And the author of TuxMake, the initial author, like right now there are many people who are contributing, like, but this project was started by Antonio Tercero, who is a long-time Debian developer, who is also part of Linaro as of now. And that's how it started. So what is TuxMake? TuxMake is not for building operating system distributions. It is specifically used in order to build Linux kernels. Now you may ask, like, what is so very different what TuxMake does in order to like build Linux kernels? Because already Linux kernel source has the potential to, provides the build tools. Specifically, we know like any free software project or things, we have this thing called Make, which is a proven way in order to like do your builds and stuff like that. So Linux kernel has Make. So it's just about like, if you want to compile Linux kernel, it just make DebConf, and you choose the different configurations which you want, and then do a make. It's that simple. But there is some complications involved. Where it gets complicated, Linux kernel supports different architectures, and it could be built with different tool chains. So you can see the architectures, most of them which are existing today. So you see i386, ARM64, PowerPC, Spark, RISC-V, Long Arc, which is the latest which has come in. As we say, saw yesterday in Jonathan talk, it said like it's a replacement mostly for MIPS. Similarly, like we have different tool chains. We have GCC, Clang. Right now, like Linux kernel also like supports Rust and LVM and things like that. And there are like, too many configurations. The configurations like DebConf, distro configs, all mode configs, random configs, and whatnot. Like there are different things and targets. So you can build a kernel image, you can build the DDBS, you can build the modules. There are different things, and apart from that, there are like build-time validations. So it's similar to the make check which happen, and there are like different tools for that. So when we combine all these 5 things, which is listed over there, now there are like too many combinations. Now this is where like TuxMake comes in and plays an important role. A kernel engineer is not just happy about getting his patch out in the kernel tree and then be satisfied. Because Linux kernel is not a piece which, or the kernel which supports just 1 or 2 architectures. It has to be compliant, or like it has to run on different platforms, different architectures in a sense. So in order to do that, a kernel engineer, when he comes up with a patch, now if he wants to like test it on different architectures, he has to do all these builds on his machine and then like validate whether his patch is perfect and works and it's not regressing on different architectures and see that thing. So usually what kernel engineers do is they maintain their own build scripts. So in order to, these build scripts, they range from like shell scripts to Python scripts, and these days like Rust scripts, in order to like maintain different kind of builds which they want to make. So say for example, he comes up with a patch, he or she comes up with a patch and says, I want to like test this patch in x86 with Clang 16. So he'll have a separate set of build scripts. Similarly, for each and every combination they used to maintain. And there is no common way of doing this within the Linux community. Now, this is where like TuxMake comes in. So we provide a way in order to build Linux kernel across architectures and across tool chains and all the combinations which you see here. So this is a support matrix which we support as of the latest release of TuxMake. So you can see all the architectures which is listed there in the from the previous slide, and all the tool chains. It ranges from right from GCC 8 to GCC 13, which is the latest, and Clang 10 until Clang 17, and we also do Clang nightly, Rust GCC, Rust LLVM, Rust Clang, and LLVM 17 and nightly. So there are few things due to, there are a few combinations which won't work, and they're not like valid configurations where the Linux kernel has to be built, and there is no mandatory stuff in order to build those. For example, you can see MIPS. We don't support MIPS on GCC 11 and 13. That is because like Debian stopped. We are not like working on MIPS anymore. So MIPS with GCC 13, GCC 13 is the latest one in Debian 12. So that combination is not supported. Due to these kind of reasons, there are few combinations which are not supported. You can also see like on the toolchain, on the architecture.
1, 2, 3.
Yes.
May I help you?
Yeah.
Should I put this in the pocket? This one? So,
Hello.
yeah.
Hello. It's audible? Yeah. So what TuxMake provides, TuxMake basically, as you said, like it's a command line interface. So it provides a consistent command line interface, and you can specify what to build, and TuxMake does the build. So we do provide like curated containers, both for Docker and Podman. Like it's basically Docker containers, which could be used both in Docker and Podman environments in order to make the builds. And the key thing here is it also helps not just the kernel developers workflow in order to do builds in different architectures and stuff. It is also reproducible. It's also aids in helping to reproduce these kernel builds, which could be like passed in kernel mailing lists and different ways in order to share things, which is a problem in an era like when TuxMake was not existing. So that's what is meant by reporting builds made easy. So even these days, if you see like people from Linaro, like in the kernel mailing list, we do report these regressions in each of these commits which comes in Linux kernel for different commits which has been made. So we also like pass the TuxMake command in order to reproduce that specific regression which has happened in the in each of the kernel developers local environment. So how it's available, TuxMake for installing? It is available in PyPy as a Python package. So let's say like the latest version of TuxMake is 1.19.0. For this talk, so whatever we are doing is based on like 1.19.0. So there are like older versions, probably there are like less features in older versions, and probably the newer versions will have more features. But this talk is specifically addressing with 1.19.0 of TuxMake. And there are other ways. I mean, I am not going to get into detail how to install it with pip and stuff like that. It's usual process how you install a Python package. And there are other ways like the distro packages. We do provide like deb and RPM packages, which is available in tuxmake.org/packages. If you go to tuxmake.org, you have the installation instructions on how to install it. And we do sign it properly with our keys, GPG keys, which is specific to TuxMake, and then publish it. So this about TuxMake. And there is another way of running TuxMake if you don't want to like install anything on your machine. So there is other way. You download the source of TuxMake, and then there is a run executable, which is basically a shell script, which will help you in order to like just run TuxMake on the fly. So that is also possible. And more details you can find it in tuxmake.org in the installation manual. So before getting into things, let me show you a simple example of the TuxMake help. So this is a command line interface which we're talking about. So this is a help. So TuxMake takes options and combination of variables and values. So the important things are like you can see the target arc. So you can specify to which architecture you want to build. And the other thing is you can pass different kernel configurations. It accepts both local files, and also you can specify URL over there, which will come in a bit. And you can see the hyphen toolchain, which provides you a way to specify for in which toolchain you want to build. And we also support runtimes. So there are like three kinds of runtimes. One is null. The null runtime specifies that TuxMake runs within your machine with using the toolchains and the architecture support which your machine or local machine supports. Now the runtime, if you specify as Docker or Podman, it is going to use Docker or Podman in order to like get the containers and do the builds. We'll get to that in a bit. So these are different things, and also you can pass other environment variables for which will be used at the time of like building the kernel. So this help of TuxMake an overview. So as I said, like I have TuxMake the latest version. So it's 1.19.0 installed in my machine, and I'll use that for all the demos. So let's start with a simple build. How we do a simple build? It's just about like saying you need to have the Linux kernel source tree in your machine. Within the source tree, so right now I have Linux 6.5.2 RC2. Yeah, I'll just zoom it. So I have Linux 6.5 RC2. I mean any Linux kernel. So I just for this demo, like I'm taking this. So the entire source is with me. I just say TuxMake. This is the simplest way you do a build. Now I'll explain like what this will do. As soon as I fire TuxMake, it's going to like do the make with the configurations provided. The first line, right? You can see it says this is the reproducible part of it. So it says like what it is doing. If you want to like pass it on to someone else, you can just paste this command line to people so that they'll also like do the same thing. So if you see the first line says the target arc is x86-64. This is a default because my machine is a x86-64 machine. And then the toolchain is GCC, which is what which is installed in my machine. And then it sets different things: the build timestamps, some k build variables, and also the default kconfig used is DebConf. So this is how the thing ran. You can see the runtime; it is null. Just I fired TuxMake. I'm not using any runtime like Docker or Podman, which I'll show an example how it works. So let's go by one on how this build is actually being done. Just before starting this presentation, I did made a build, so I'll walk you through that, how it works. So the same thing. So the first is the reproducible script, or what this command is going to do. So it's going to build by default. If you don't specify anything, the make targets, which will be used as config, default, kernel, XAP kernel modules, DTBS, debug kernel headers, everything will be built. And you can like pick and choose what you want to build, which will come in a minute. So what happens is all the builds will be done in a dedicated build directory, which is under your root, your home directory in .cache within TuxMake builds. So that is where all your build will end. Also, you can specify if you want to build it in a different directory. So that's where your end artifacts will get into. As you can see here, so it's going to do a DebConf build, and then it will also fire the BC image for this build. And since we have requested modules, which is the default, so it's also going to build the modules, and then it will also create a VM Linux image, which is a compressed image, and also like compresses it, and then put it on the build artifact. So there'll be a build number within this, within the builds directory, and within that build number, like your artifacts will go. So at the end of this build, once it's completed, it will also show the time it took in order to do these builds, and what was done and what was not done. So if you see config, the make target config, default kernel, all those things passed, which was done, and XAP kernel was skipped because probably I'm not having the tools required in order to do that in my mission. So modules, of course, it did. So DTBS, it was skipped, and debug kernel and headers were done. And these are the time it took in order to do all these builds. So let's see what is there within the builds directory. So the artifacts end up here. If you see here, these two things, build debug.log, build log, these three things basically, build.log and metadata.json will always exist, even if your build fails, in order to see what happened in your build. And metadata.json gives more information about the different things that were used within the build. And you can see the BC image got created, and the modules as requested was done, and VM Linux was generated, and it is compressed just to save some space if you're doing like multiple builds in your mission. And what is the config used and stuff like that. And there is a system map that got generated, and the headers, again, it is compressed after doing it. So this is what happens within the build. As you can see, like the different steps it did as part of the build. Okay, we just saw like what was done within the build. This is a summary in the build which I just shown. Let's get into the metadata.json which was produced as part of the build. So if you see like this JSON had the artifacts, and you can see like the modules which were built as part of the build which we fired, and what are the environment variables set. So we have the host as TuxMake, host variable as set as TuxMake, kbuild host, and the timestamp, the exact timestamp when the build happened. The kbuild user, again, it is set as TuxMake. You feel free to, set it. There are options in order to like manipulate with this, and KC flags which were used, and jobs represent the number of threads. So 8 threads were used because my machine is capable of that, and probably like if you have a even powerful machine, like the number of processes you have, like so many threads will be. It's basically the make variable or the number of parallel things that has to happen in make. And the kconfig is defconfig. You can also add like kconfig using kconfig add more kconfigs if you have a requirement for that. So the reproducer command line, so this is represented in JSON. So you also have that as soon as you started the build. So the first line was the reproducible command which you had. And the runtime used, as I said, this build was done within my mission. So it used a null runtime, which denotes the host in which I'm running TuxMake. And then the target architecture was x86-64, and the targets that were built was these things. Some of them have been skipped. And the toolchain used was GCC. So we didn't, it was a silent build. We didn't provide verbose option. And there are more details about the compiler used. So it was GCC 11, which was there in my mission, and the full version of this compiler. And hardware, I had 8 cores, so that's why the jobs were run 8 cores. And the OS which was used, the resources, like how much disk space was actually used, and other results on basically what the artifacts that were generated. So all these information are here, and also the relevant durations for each of these are durations with respect to different steps which TuxMake did. So it took 462 seconds for the build, and then like cleanup, copy, different times. And if there are like more intuitive things like if there were errors for some reason the build failed and there were errors on warnings, those will be listed as part of this metadata JSON. And overall the build pass, and this is what has come in the summary at the end of the build, which we saw previously. So as you say, like errors and warnings are part of this metadata. And it also speaks about the source. If you're building from a kernel tree, it will give you the git commit hash and which repository it came from, and all those things are accumulated here. Since I downloaded this kernel source from kernel.org, there is no like commit details, but of course the tag of which version of kernel which you have built is there, and the system app offset has been there. And the other tools involved during this build, so you can see the Flex, Bison, all the versions of them to give you like more insight on like how this build actually happened, and the TuxMake version which was used, and the kernel on which this build was carried out, and things like that. So this is this metadata has like all the information in order to see how this build and how this build was carried out in a specific development environment or in a specific host. So this will be useful when you want to like compare your build with others. Now this is not the reproducible part. So this is the metadata in order to see whether there was any differences. Okay, so let's move on. Now, I was telling like this is not about like building in your machine, which we saw a simple command, like we just fired TuxMake and it did a build with whatever tools that were existing in my machine, and then doing the build. Now, if you want to do cross toolchain kind of builds, now this is where the Debian part comes in with respect to TuxMake. So say for example, I want to do a build for specific toolchain, say Clang 11, and for a specific architecture. So what I do is I fire the build like this. Okay, the build which we fired as part of this talk also completed. So let's see another build. So I'll say target arc as say ARM64, and then toolchain as say okay, let's take GCC 9 for example, and what else? And I'll say the runtime as Docker. Okay, now there are two runtimes. I'll come to it. So now I fired this build. So what I'm trying to do is I want to do a kernel build for ARM64 with GCC 9 toolchain. When I fire this, so since I've specified Docker runtime, it's pulling the TuxMake /ARM64 GCC container from Docker Hub, which is the default, and there is another repository where you can pull these images, and it pulls this image and does the build within that container. That is the TuxMake /ARM64 GCC 9. So this ARM64 GCC 9 container is something which is published as part of the TuxMake project, in order to like which will be loaded with all the cross toolchain tools which is required in order to carry out the build for ARM64 on with GCC 9 toolchain. So that's what is happening. The rest of the things are same. So you have the reproducible thing, what it is doing. So as you can see, the target arc is ARM64, and then runtime is Docker, and which Docker image was used. And you can find more information about this Docker image in the metadata.json. It will give the hash or SHA-50 256 sum of the Docker image which was used for this build. And the rest is the usual procedure. The only thing is this build right now happens within the container with all the cross toolchains loaded for that specific architecture and toolchain. So that's how it works. So people who are familiar with containers know like what Docker does, and nothing different. Podman also uses the same images. Podman is something equivalent to Docker. The only thing is like Podman doesn't require root access. It's a rootless environment, and also it doesn't run as a daemon, just how Docker does. So there are like two different ways people use the containers. One is Docker and another Podman. Both of these we support as part of TuxMake. So as he said, like there are like multiple ways. So all these combinations could be done. So you can choose the target architecture, tool chain. You can build using different k configs by passing those with relevant options. So as you can see, you can pass config cas and also set the environments using -e option, the environment variables which you want to pass to the Linux kernel builds, which you do. Okay. Sure. So it's the default is it creates the build artifacts within .cache of your home directory within TuxMake folder. Within that you have the builds folder. That's where it goes. If you want to specifically say a directory where your build has to go, build artifacts has to go, you can use a -build-dir option in order to put your artifacts there. Now this is where incremental builds comes in. So if you specify this, the next time you do some, edits to your k configs or different stuff, and you specify the same build directory, it's going to do incremental builds. It's a usual make process, how incremental builds are being done using make. So specifying the same build directory is going to fetch you like incremental builds. Let's come to the reproducibility part. So as I said, TuxMake helps in doing reproducible builds. So how it is possible? So the high-level reproducibility which you're talking about is you can pass this TuxMake command to any person, and then say like this combination with say RISC-V and say Clang17 with this commit hash, in the kernel source tree, I had a regression. Can you check this? And then like you paste this command to people so they can run it. If you pass the runtime as Docker or Podman, the same container is going to be used, and then like you can make it reproducible. In a way, like what you have built is going to be same as the other person has built, but it's not like full bit by bit compatibility of the builds which is done. The kernel itself provides a way in order to do perfect, full, bit for bit reproducible builds. So that is done using kbuild build timestamp, kbuild build user, and kbuild build host. So if you pass these three things inside your TuxMake builds, and you know like I've shown you the -e option, which is the environment variable option. So if you give the same timestamp, the build user and host details, so the same build is going to happen, and it'll be bit for bit reproducible builds. Everything will be same. Okay, so this is an example how you do it. So you pass the kbuild timestamp as like this, the user TuxMake and kbuild host. It could be anything depending upon how you made the build using TuxMake. Not necessarily it should always be TuxMake user. So, and for that sake, like the Docker image with the SHA is also provided. So when you do something like this, the BC images and all the artifacts which is being produced will be full bit by bit compatible, and it will have the same hash. I'm not going to demo it due to lack of time on this talk, but this is how you do it. And you can read more about like being more specific about reproducible builds in that URL. So these slides will be available, so you note it down. Like probably you can revisit later to get these URLs. Okay, so this is the Debian part where why this was possible, because Debian supports many architectures which the other distros don't support, and it's been quite some time which Debian provides this. So because of this, it was possible. So all the architectures which Debian supports and the tool chains, since Debian has all the tool chains which is packaged, so we were able to like come up with these combinations. It's just about like picking a base Debian image and then install, get the required tool chains and the architecture, cross-compiling tools for the architecture, and then come with a container image, push it to Docker Hub, and also we also have a public repository, ECR mirror, which is gallery.ecr.aws, with a search term TuxMake, where you have the same images. And all these Docker files which are used in order to build these images are available as part of the TuxMake sources. And this is built on top of Debian's base image, which is provided by Docker Inc. And you can verify everything. So there is no extra things which we are doing out of it in order to generate these Docker images. So that's how it was possible. Since Debian has support for so many architectures and everything is packaged, so we are like curating these containers and publishing it. We have almost like 260 to 270 containers which is being published for all these combinations which we are talking about, which enables making these kernel builds possible for different tool chains. It makes the workflow of kernel engineers and whoever want to do cross-compiling of kernel in different architectures, their life easy. And as I said, it's not just command line. TuxMake could also be treated as a library. It's a Python library, so it's just simple as that. So you import tuxmake.build, and then you say build with your kernel source tree path, and then all the options which you have in TuxMake command line could be passed as a parameter to this, and you can make it. So this will be useful if you're coming with some Python script to run in a CI to make kernel builds. This will be very useful. So contributing, the documentation is available in tuxmake.org, and we host it in GitLab under the Linaro institution account. And then we have issue tracker. We again use GitLab's issue tracker, and the contributions should be sent as merge requests. Anyone is welcome to contribute. And there is a COC, you can go through it on that link of TuxMake. And of course, it's MAT based tool. And these are references. We have, all the documentation. There is a yearly article in LWN regarding TuxMake, how it works, and how we came with this stuff. So you can see that. Probably like it's a bit outdated, it's 2 years old. So the latest developments may not be existing. But that's a thing. And also there were like discussions regarding this in Linux Plumbers, I think back in 2020, so where like you can find more information. And there is one commercial thing which I want to like, this is not related to Debian or whatever, but we also provide something called, as I said, TuxSuite, which is TuxMake is part of the TuxSuite kind of things. So TuxSuite provides tools like this, a lot of tools like this. We have this TuxMake is specific to building kernels. And if you want to do builds in a large scale, so we have a backend which is running on the cloud. So you can make use of this tool in order to fire for all these combinations within the backend. So basically we use TuxMake in order to do this on-demand builds on the cloud in an ephemeral environment, so that people can run their CI or regular builds, and they can even do like bisection of kernel trees in order to see where it has regressed, all these kind of things. So you can make use of it if you have a crunch for hardware and things like that. So, and a lot of people are using it. One of the main uses is like there are two people. One is Clang Build Linux community, which is using TuxSuite. So they have a subscription-based stuff, and also LKFT, which is Linux kernel validation, functional testing project, which is forefronted by Lenaro, which has been using this, and we do almost like 300 to 400,000 builds on a monthly basis every month for different people. And also, if you want access to TuxMake, we can provide it for the community. So you can contact us at tuxsuite@lenaro.org in order to request for an account. So we can provide that too. And that's it. Thank you. I'm open for questions.
So still we have 2 minutes.
Okay, I'll ask a question. Do you think we can test Debian kernel with this tool? Would be very hard to integrate, or?
Yeah, I mean, we do have, TuxMake is one thing. We have similar things like TuxBake, TuxRun. TuxRun is basically for testing kernels. We provide QEMU images similar to this concept, but it's plainly used for testing. So you put your kernel, you point the kernel, specify the architecture, there's a QEMU fired for it, or you can also do that with the help of Lava, if people are familiar with Lava. So you can fire k-self-test, k-unit test, and different kind of things. So any kernel image, put it to TuxRun. So you can visit tuxsuite.com, which lists all the tools which we provide. So TuxRun is what you need in order to run tests.
Yeah, and do you think you can build some other software rather than kernel?
Yeah, we also like provide TuxBake, which is used for building Yocto, Open Embedded, Android, and different stuff in a similar way.
You said that to build the kernel in Docker image, so we have to fetch the Docker image from the Docker hub. Is it possible to host that image in our local environment?
Yes, you can. So all the Docker files are part of the TuxMake project source. So if you want to build that, so as I said, like we provide a ECR gallery.ecr.aws. So that's basically like something which we publish from with our own accounts in AWS. It exists for a reason, because Docker rate limits recently after 2021. So there is like a limit of 100, and it goes exponentially. So they rate limit things. So that's why we provide a AWS mirror of these images. So if you want to host that, like of course you can, you're available, you can do that.
Hello.
Yeah.
I didn't quite get one part. If you want to use the Python interpreter, how do you use TuxMake using the Python interpreter?
Pardon me, Python interpreter?
How do you use TuxMake if you want to use it through Python?
Yeah, you can import TuxMake as a library in Python. So that's what I was telling, like import tuxmake.build. So that's going to expose you all the modules and different APIs which is existing in TuxMake. With the help of that, you can write a program in order to run it in Python.
Okay, thank you.
Hi there. Those cross-compiler tool chains in your Docker images, how do you generate those? Do you have a tool or something, or do you just run some shell scripts? Or what?
I mean, it's just defined in the Docker files itself. So for each of these combinations, like what are the tools required for cross-compiling? It's just an apt-get within the Docker files.
Okay, fair enough.
Which comes from the Debian repositories.
Okay, thanks.
Okay, well, thank you very much. Thank you, Senthil, for the presentation. I think we have a break now for lunch, so enjoy.